Okay, let's look at question number 2. So this is question number 6 from the 2006 AP administration exam, but it's question number 2 on your review. So this says that a car travels on a straight track during the time interval 0 to 60 seconds. The car's velocity measured in feet per second and acceleration measured in feet per second, or feet per second squared, are continuous functions. So that means we can integrate them. The table above shows selected values of these functions. So part A says using appropriate units. So we need to make sure that we are using the correct units. So that's going to be at least a point. We can lose a point there on our FRQ scale and all that. Explain the meaning of the integral from 30 to 60 of the absolute value of v of t dt in terms of the car's motion. Okay, then it says approximate that integral using a trapezoidal approximation with the three subintervals determined by the table. Okay, so this is a two-part for part A. Using appropriate units, explain the meaning of the integral from 30 to 60 of the absolute value of v of t dt in terms of the car's motion. Okay, so if we are integrating velocity, we have absolute values in here. So remember, we just talked about this, like displacement and total distance traveled and all that stuff. Absolute values, it matters where they are. When they're on the inside of the integral, that is total distance. So part A, the integral from 30 to 60 of the absolute value of v of t dt is, so let's explain what this is. It is total distance. Because those absolute values are on the inside, it is the total distance and how is our distance measured? So let's look back up here. We are talking about feet per second. So if we're talking about distance, then it's going to be in feet because it said to have units. So there's our units in feet. That we're talking about the car. So what happened to the car? Well, the total distance in feet, the car traveled. And we're looking at this integral, and we're talking about 30 to 60. So we're also saying from 30 seconds to 60 seconds. So that's our interpretation of the meaning. Now it says approximate that integral using a trapezoidal approximation with 3 subintervals. So we're looking from 30 to 60. So this table goes from 0 to 60, but we only need to look from 30 to 60 for this problem. So we will have one from 30 to 35, from 35 to 50, and 50 to 60. So when we are doing this, when we are taking these absolute value bars, this is a little bit different than we've done before. We're taking the absolute value of the velocity. So when we choose these areas for velocity, we are going to be working with the absolute value of those. So when we write our sum, our trapezoidal sum, our area is going to be 1/2. We're going to have 3 subintervals. So 1/2 times the height, and then base 1 plus base 2 plus 1/2 times the height, and then base 1 plus base 2 plus 1/2 times the height, and then base 1 plus base 2. So let's look at the heights first. So if we're looking here, 30 to 35 is 5. 35 to 50 is 15. 50 to 60 is 10. So 5, 15, 10 are my heights. So 5, 15, and 10. And then I'm going to take the absolute values of these here. So I'm going to have 14, plus 10, then 10 plus 0, then 0 plus 10. So I have 14 plus 10, then 10 plus 0, and 0 plus 10 again. When I multiply all this out, I have 60 plus 75 plus 50, which gives me 185. And 185, this is total distance traveled in feet. So I need to make sure that this says feet. And there we go, part A. We have determined everything we need to determine. If we look at our rubric, so this is what the AP scores with. So we said this is the distance in feet. We said in feet that the car travels from t equals 30 seconds to t equals 60 seconds. We just said 30 seconds to 60 seconds. That's fine. We have an explanation. So we have that first point. Trapezoidal approximation, we have 1/2, 14 plus 10 plus 5. 1/2, 10 plus 15. Plus 1/2 plus 10 plus 10. Remember, this is an FRQ, so we could have stopped there and just said feet. Okay, but once we get that value, there we are. And we have that value. So let's look at part B. Part B says using appropriate units, so let's not forget units, explain the meaning of the integral from 0 to 30 of the acceleration, no absolute value this time, in terms of the car motion, then find the exact value. So we're not approximating like we did before. We are finding the exact value. So part B, we need to think about the integral from 0 to 30 of the acceleration. 30. This is, so it's the change in whatever the integral of the acceleration is. So this is the change. Well, the integral, if we integrate acceleration, we get velocity. So it's the change in velocity. Velocity of what? Of the car. It says units. So what is our velocity measured in? Well, our velocity is measured in feet per second. So we can go say that down here in feet per second. And where are we looking? It's from 0 to 30 seconds this time. So there's our interpretation. Now we need to actually find this integral. So if we integrate, from 0 to 30, the acceleration, dt, well, we said it was the velocity. So the velocity of 30 minus the velocity of 0. Well, we can go back up to our table and get those values. So even though we don't have an equation, we can still integrate this. So the velocity of 30 is -14. The velocity of 0 is -20. So I have -20 minus, wait, backwards. The velocity of 30 was -14. Minus the -20 goes over here. So that's -14 plus 20, which gives us 6. 6 what? Well, we just said the velocity was measured in feet per second. So let's look at the rubric for part B. Part B says, is the car's change in velocity, got that, in feet per second from t equals 0 seconds to t equals 30 seconds. Explanation, got that point. Value, did we get all the way to 6? Yes, we did. We could have stopped here as soon as we plugged in values. Okay, so we are good there as well. Oops, wrong way, sorry. That's the next question. Next, let's look at these next two. They're very similar. It says for 0 to 60, so we're looking on the interval on the table. Okay, well, we're looking at the table. Nice to know. We've been doing that the whole time. Must there be a time when the velocity equals -5? Justify. And our next question is kind of similar, so we're going to think along the same lines. Must there be a time when the acceleration equals 0? Justify. Okay, well, let's think about this. Must there be a time when the velocity equals -5? Well, if we look at these values, we know that they're continuous. So if one of the values crosses over -5, we know it has to be in between there, and we're going to have to talk about what theorem that says. But -5 wouldn't be in between these two, wouldn't be in between these two, not in between -20 and -14, -14, -10. Nope, -10 and 0. Oh, -5 would be right in between here. So, yes, our answer to part C is yes. And here's how we're going to write that. Since we know, if you look back up at your table, that -10 happens when at time 35. So V of 35 is -10. And the 0 happens at V of 50. So, and the velocity at 50 is 0. And we know they're asking us about -5, and -5 is in between -10 and 0. So we'll just say that. I mean, obviously it is, but we'll just make sure that everybody knows. -10 is smaller than -5, and then 0 comes next. So this says that -5 is in between -10 and 0. Then, so this is our no-duh. The number is in between. That's our IVT theorem, intermediate value theorem. Intermediate means in the middle value theorem. So then we don't have to write, oh, I already wrote then. V is what I was going for. IVT, you can write out intermediate value theorem, or you can write IVT. You do not have to write out all those words. Guarantees that there must be a time when V of t equals 5. So that's that whole question. -5. I'm sorry, we were working with -5. So let's make sure that we let's make that like really clear that we know that we're talking about -5. There we go. So yes, since we have -10 and that time is 35, and we have 0 and that time is 50, and -5, so those values on the outside, -5 is in the middle of that, then we have the intermediate value theorem that guarantees that there must be a time when the velocity is equal to -5. We don't know what that time it is, but there's some time where the velocity is -5 because it has to connect. Let's see if we got all of our points. So it says yes. So they said it a little bit differently than us. They strung it all together, but we ended up saying the same thing. We said that there is a velocity that's equal to -10, and there's a velocity that is equal to 0, and -5 is in the middle. We just said it a little bit differently, but we got that point. And we said yes, and we mentioned the IVT. I don't know what that hypothesis point is. If you want to go for that, go for it, but I don't really know what they mean by that. But pretty much it's just IVT. That's what you need to, the intermediate value theorem, that if you have a number and another number and the function is continuous, it's going to pass between all the numbers in the middle. Okay. So let's do part D. Is very similar. Part D, must there be a time when the acceleration equals 0? So now we want the acceleration down here to equal 0. Well, we want to think about this a little bit because I had a little bit of trouble with this because it's going to be a little bit different than our velocity problem. Okay, so just looking at this, thinking about how we did the intermediate value theorem before, we wouldn't say that it was 0 because none of these cross over 0. But that doesn't necessarily rule it out, because couldn't something go from 1 to 0 and back up to 5? It could, but 0 is just not in the middle there. So that was a nice little theorem that we had that was easy to use because the information they gave us, it was easy to point to that. But here, we don't see it immediately. Our first reaction, if we were thinking about IVT, would be no. But the IVT doesn't say if it doesn't, then it doesn't, because it can. The IVT is just a specific little part of that. So if we think about this, the acceleration is going to be equal to 0 anytime that we have an extrema, okay? Or if we have a time where we have a velocity, the derivative of our acceleration is our velocity. So our velocity is equal to each other, I'm sorry. That would mean that there's a time in there. We have a theorem that says that there is a time where acceleration would equal 0. So this one's a little bit harder. I know that was kind of hard to follow, so let's write it out and be able to understand what's going on. So D, the answer to D is actually yes. But it's not by the intermediate value theorem. It's for a different reason. The reason why is since if we look up here and we look at velocity, well, is there any time where our velocity is equal to each other? And in fact, if we look at velocity, well, it's -20 here and -20 here. So the velocity at 0 is equal to the velocity at 25. So let's start there, okay? The velocity of 0 is equal to the velocity of 25. Then we have the mean value theorem. The mean value theorem guarantees spelling that is not easy, that there must be a time t in, so what we're looking at is we know that it's definitely going to be from 0 to 5, or 25, I'm sorry. From 0 to 25. When the acceleration is equal to 0, because we have to just note that the reason why this is because the derivative of velocity is equal to the acceleration. So remember, in case you're having trouble with this wordy explanation, our mean value theorem says that f prime of c equals f of b minus f of a all over b minus a. Well, if we think about this, whenever these two things are equal on the top, if we had the same number minus the same number, it would simplify to 0. And 0 divided by any number is 0. So that's the derivative at that point. It's equal to 0. Well, this is what we are using to say, wow, since we know that these two times on the velocity are equal to each other, when we subtract them with the mean value theorem, we will get 0 on the top. And that guarantees, the mean value theorem then guarantees that in between those two, there is a place where our derivative equals to 0 for the velocity, and the derivative of the velocity is acceleration. So we know we're connecting those two in that way. Okay, that's probably the hardest abstract concept to get. So maybe you wouldn't have gotten this point on the AP exam, but that's fine. okay? We don't have to get every single point to pass it, but we do need to do our best. So let's see, it says, yep, they set them equal to 0 by the mean value theorem, guarantees that in 0 to 25, since those were the two things that were equal, your acceleration is equal to your derivative velocity, so that's equal to 0. So they said you had to have that those two things were equal because that's what makes it a special case. And your answer is yes, and you refer to the mean value theorem. That's how you get all those points.